Okay, let's look at another programming pattern that gives rise to a family of higher order functions. That's the programming pattern where you take a list of things and you want to combine all those things together in some way. So the result is obtained not by applying an element to each individual element, but by some arbitrary way of combining the elements. So let's take an example of such a function which illustrates that pattern. If we want to sum up the elements of a list, sum of the elements of a list, I'll just check the sum is in scope. The sum is a function which for any list of numbers adds all the numbers together. A typical combining pattern. So one way of defining sum, if we were to define our own sum, would be to say that the sum of the empty list is 0. Sum of a list which starts with a number n and continues with some numbers will be n plus the sum of the rest of the list. And that would be an example of how you might define sum, combining all the elements of a list. Another example might be the function AND, which you may have come across. It's a function for taking a list of Boolean and applies the AND operator to that list of Booleans. In other words, it checks whether a list of Booleans is true, all true. If they're all true, it returns true. If any of them are false, it returns false. What would you expect AND to do on the empty list? Somebody suggested false. That might be a possible answer. Somebody said true. Maybe it should give an error. So what is the sensible thing to do for an empty list? Well, let's go back and look at the sum. What's the sum of an empty list? You're sure that it's not 1, right? So why do you feel that it's okay that the sum is 0? What's special about 0 with regard to the sum operation, to the add operation? It's the identity element. It's the element which doesn't change what you have. When you add 0 to something, you get back the thing you started with. So it's the identity element for sum. So that suggests then that the AND on the empty list should be the identity element for the Boolean AND operation, and that's the value true. If you take true and something else, the answer is always the something else. So we could define the AND function in a very similar way to the way we define the sum function. In the base case, we get the identity element, true. In the other case, when we have a Boolean B and a list of Booleans, we use the binary AND operator to combine B and the rest of the list. So you see that the two functions here, sum and AND, have a very similar pattern. They replace the nil with the base case, the appropriate base case. And they replace each constructor, each cons in the list, the operator colon, which builds a list, they replace that by the combining operator that we're interested in using to combine together the elements of the list. So the generalization of this is a combining function which takes parameters. This is called, the combining function is called foldr. It folds from the right. We'll see what that means a bit later, but it takes as its argument the combining operator, that's the first parameter. It's not really an operator, it's just a function, but we're going to think of it as an operator. And it takes the base case, the identity element for those operations above, but it's just the base case. And what it does, when given the empty list, it simply returns the base case. When given a non-empty list, so we apply it to some non-empty list x followed by x's, it combines x using the operator op, and I'm going to actually write it as an operator by putting it in backticks, but we don't have to, and the recursive folding of the rest of the list. So you see how this generalizes the pattern of the above two examples. So how would we write sum and using this more general fold operation? If we want to fold using the function sum, we put it in brackets, we get a function. The base case is 0, and we fold. Okay, what's happened here? Well, I've used the name foldr prime, and it's not a little bit unclear which foldr I meant. There is actually a standard function called foldr prime. If we want to do, for example, product, then the base case, the identity element for product is 1. So if we want to multiply the elements of the list together, we can use we fold with the multiply operation and base case 1. Now, fold is very powerful. There are many things we can do with fold, and actually there are a bunch of different varieties of folding functions according to the order in which you fold the elements together, and whether you actually have an accumulating parameter, whether you have a base case or not. So typically, for example, when you define the sum operation, you would fold from the left rather than from the right. Okay, we've seen how several common patterns of computation can be turned into a higher order function so that the pattern of computation becomes an actual function, and we use that pattern by supplying the right arguments to that function. So in today's lecture, in the remaining parts, we're going to see how more examples of how we might generalize common patterns of computation, how we create higher order functions because we recognize the common pattern. And the second thing we need to understand is how to feed those higher order functions. In other words, how to find good ways of providing arguments to our higher order functions. So one way we can do that is we already know the name of a function that we're going to feed to our higher order functions to build new functions. But there are lots of other ways of doing that, and we will see at least 4 other ways of building functions rather than just defining a named function or using an existing named functions. So let's start then with an example of how we might use some of these patterns. And it's a function called onLines. And I've defined here a little verse. It's just a long string with new line characters in it. It's one big string. And a very common thing that we do with strings that we receive from files or from input is to actually display them as a bunch of lines. So what actually happens when you print out the verse using putstroke, when you display it on the screen, the new line characters actually cause the line to be broken and displayed on the next line. Now, onLines is a function which takes a string and splits it up into actually, no, it's the function. We got the example wrong here. It's the function lines that I'm thinking of. So the function lines takes one big string and splits it up into its individual lines. So the lines of the verse were all the things between the new line characters. onLines is the dual of that. It's the thing which joins together a bunch of strings by putting a new line in between them. And that's the relationship there between onLines and lines. Very useful functions. So what kind of computation pattern is an onLines? So onLines is an example of a computation pattern we've just seen, namely combining things together. So onLines, the reverse of lines, joins strings together by jamming a new line character in between them. So in order to define this using fold, we're going to need a little function that does exactly the gluing job that we want. We don't have a standard function to do that, so I'm going to define one. And I'm going to call it join new line, join NL. So the combining function we need to define in order to define on lines. And the base case I'm just going to take to be the empty string. So we don't get anything more than the empty string if we give an empty list of strings. Now I'm going to define this locally, and the join NL will take two things. They're going to be strings, a string on the left and a string on the right. And what it's going to do is take the first one and join it together with the second one, but with a new line character in between. So that's one way we could write that. Nice symmetrically, we join S1 and S2 with a new line character between them. So that's the folding, that's the function we're going to use to fold together to define the standard function unlines. Okay, we get an error here because unlines is already defined. So my normal practice would be just for the sake of demo, put a prime character on the front to get a new name, and then I should be able to compile the function. And you see that my version does indeed the same thing that you would expect to get. And so this is one way to feed a higher order function, is to define the function you need if you don't already have it, and provide it to the higher order function by naming it. And we're going to see lots of other ways.